Welcome to this Simio tutorial. In this tutorial we are going to model a seaport. That means we have some freighters which arrive. Then the freighters are going to stack up in the ocean and the harbor master docks them. Once they're docked, they are sink. So these are three nodes. They are implicitly already connected because in Simio the entity goes to the closest node, but we can be explicit and don't have any ambitious paths. So if we double click, we can continue. So with the Alt key, we can, with the middle mouse key, we can move it and zoom in and zoom out. Another connector. Okay. So let's just make a note that this is supposed to be a seaport simulation. So floor labels are quite good to make these comments. So seaport simulation. Okay. And we have got freighters that arrive. Freighters arrival. Let's rename the cell as well. So this is always very important to have some good descriptive names. So this is the docking process, and eventually the freighters are docked. Freighters docked. Okay. So in the arrival process, we have got freighters that arrive. Right now we have got the default entity here. So let's change that and put in model entity and rename that to freighter. Freighter. Okay. So we see immediately it's updated in the entity type, which is great. Moreover, we see the interarrival time here as exponentially distributed, and we see it's in minutes. So let's see what example do we want. Let's say in our example we have got 3 freighters which arrive per hour. So again we should make a little note. I could just copy that, or again go to drawing and insert a floor label and say 3 freighters arrive per hour on average according to a Poisson process. On average, Poisson process, which basically implies exponentially distributed interarrival times. Okay, which means every so 3 freighters per hour, that means every 20 minutes. So 20 minutes on average. Okay, perfect. So we obviously have to set the 20 minutes. So I could just go there and say 20 minutes. Perfect. There is there's a very nice way to actually put the properties in, which is in here. So you have got a summary sheet, especially if you have got lots of sources and nodes. So here I could easily put things in as well. It's a quite nice overview. Oh, we don't really need it at the moment. Anyway, so that's done. So in order to have a stable system, the harbor master who docks the freighters must be faster. So that means he should be able to dock more than 3 freighters per hour. Otherwise, the process becomes unstable. Also, on average, it looks like it would work, but if I approach 3 freighters, then everything it doesn't work so well anymore. Okay, let's copy that. Control C, Control V. Let's edit that again and say the harbor master docks 4 freighters, or can dock up to 4 freighters per hour. That means an interval time of, or a service time, not interval time, it's a service time. That means service time of 15 minutes on average. Okay, and again we say exponentially distributed. Okay. The good thing with the explanations is you know immediately what's going on without looking and searching. And here we have got the processing time. So now I'm going to open the expression editor, and here you see lots of function, and one of them is the random function, which is already right now it's a triangular distribution, but we want to have the exponentially distributed one so that we can verify it later. Okay, let's have a look. Random, and now we see there are lots of functions and lots of popular ones. Triangular, especially normal. Everyone knows the normal distribution. Airline, quite famous as well, and exponential distribution is the one which is analytically very convenient because of the memoryless characteristic property. Okay, 15 minutes. And okay, unit 15 minutes. Perfect. So let's see, does that actually work? So we can go to the run environment and see, yeah, the run is active and something is happening. There's an entity in there and it runs great. We can increase the speed, we can increase the end time. So let's say 10 days, and stop it again, run it again, fast forward, yeah, onto the end. Yes, okay, so it seems to be running. We could of course immediately look into some results, but more often, or actually almost always, we are going to run an experiment. So that means we are more interested in the statistical significance over the long run. Okay, how do we do that? So if we go back to the project home, there's this new experiment. Right now we're in the facility view, and we have been creating a model. Now we are going to create a new experiment. So we see there's an experiment for this model, and this is our first scenario. So we could put some responses and controls in there in the model, but let's say we're just interested in our MM1 system, and for statistical purposes 30 replications. It means we are going to run a simulation run 30 times. But now a simulation run, the starting time starts at a specific starting time. Okay, let's start after run and say current hour. Okay, fine, whatever that is. And the ending type is the run length which we're interested. Let's say the harbor operates 10 hours, but since we are interested in the long term of the running, we are going to run it for okay, in shifts of 10 hours, or yeah, 8 hours, doesn't matter. So 8 hours, 8 times 3 is 24 hours, so that's a bit nicer. Shifts of 3 hours, and let's say 800 hours, so 100 shifts. Okay, fine. That should lead to a nice stable, well, it should converge to a steady state, hopefully. And we're doing it 30 times, so we should get some nice results. Usually we have got a warming up period, a transient period, where the first few hours the system is going to stabilize, but we're just saying it's fine. But if there is a lot of time until it converges, then you should cut off the warm-up period to get better analytical results. Okay, anyway, let's just run it and see what happens. So it's running, great. Here we see the progress. We are 80% through already, 27 out of 30 completed. One of the scenarios runs in about 1.3 seconds, so super fast. So we could easily run it a longer time. So it's completed, great. Where do we see the results? Here in the pivot grid, we get all the responses of the system which are automatically recorded. We could of course have some custom responses as well. This seems to be quite a lot of information. So what do we actually want? So let's go back to our model. And what do we want? We would of course like to see how long does it take, or how long does a writer have to wait until it is processed on average. Well, we do know that the service time is 15 minutes. Then another interesting part is how many writers are there actually waiting to be processed, docked. Okay, so these two measures we definitely want to have. In fact, we would like to see all the operating characteristics. So how long do they have to wait? How many are in the oceans? How many are serviced? And well, we know the service time is already 15 minutes. And obviously the system time in this docking process, the altogether time. Good. So basically we are interested in server characteristics. So let's go back to the experiment and let's create a new view and say KPIs or operational characteristics. And we are interested in the server. Okay, so let's filter to the server. Then, okay, let's have the docking process. Obviously, if we just wanted to have the docking process, we could have selected it here. So same result. We are more interested in the averages. So let's say averages, average hours, and fine, let's just have that. So now that's interesting. So we've got the input buffer, which is the queue, and we see that we have got 2.21 freighters waiting in the ocean. Okay, We have got the time as well, time in station, so number in station, time in station, which is 0.73 hours. Okay, let's see whether we could have that actually in minutes. Minutes, and we are actually just we are not interested in the maximum. Total. Okay. We are not interested in minimum either, so let's get rid of the minimum. All right. So, where were we? So 44 minutes. So these are the two characteristics which we wanted to know. What else do we see? The processing itself. So on average, the processing time is 15 minutes, which we specified originally. So yeah, should be. We also see it's 0.75 0.75 entities fritters are processed on average, which makes perfect sense because it must be the utilization. Okay, we probably should have a word about that in a second. Then the total time which we have. So the total time is 60 minutes, so 15 plus 45, that's roughly 45, 60 minutes. Okay, that's fine. And the total time it should be 1 hour. Okay, 45 plus 1 hour. Let's see whether that agrees with the queuing theory. So in the queuing theory, let me open a PowerPoint presentation and make a few notes. So what did we have? We had the arrival of 3 freighters per hour. 3 freighters per hour. We had the service rate of 4 freighters per hour. So that's basically interval time of 20 minutes, service time of 15 minutes, which gives us a utilization of 3/4, which we saw as 0.75, well, which is 75%, which is fine. So this one is also the service time. Overall, from a queuing theory point of view, the number of freighters in the system is the utilization minus the idle time, idle state, which is 3/4 divided by 1/4, which means we have got 3 freighters on average in the docking process. Then in the system we have got row, so 3/4, 0.75 freighters, and that means in the queue we have got L minus LS, which should be 2.25 freighters. Okay, great. So what about the corresponding times? The system time, the service time. Well, we know the service time. That's the 15 minutes. Or we could also go into the hours part, since we have got hours here. So 15 minutes is a 1/4 of an hour. Also 15 minutes. and the queuing time. How do we get those? So luckily there's little slow, which is n equals, okay, and we actually called it L. L equals lambda customers per hour times the time times the time. Okay, so that means this is L divided by lambda. That means what is L? 3 writers divided by 3 writers per hour. Writers per hour. That means we have got 1 hour. That means we have got 60 minutes. That means the queuing time is W minus WS, which is 45 minutes. Alright, so we have just verified the system, which pretty much agrees with what we have seen over here. We have got 45 minutes. Theoretically, we have got 45 minutes. So maybe when we cut the warming up period or increase the simulation runtime, we get a little bit of a better value. We should have the half width, which covers it easily because we can add 2 minutes. So that means we are 2.6, 2.7, which means we have got 47 minutes and like 41 and a bit minutes. So we covered the 45 minutes. Again, we can reduce the half width by increasing the simulation runtime. Okay. From all these 30 replications, we actually got quite a bit of variation. So we see there's quite a bit of fluctuations are going on. So one of the simulations, also the shortest one, for the shortest 800 hours, we had an average of 30 minutes. So that's interesting. We do see a lot of fluctuations here actually. So this is why the averages on their own should never be considered, but to get some safety buffers in there, you should really consider the half width and the distribution of the results. Alright, anyway, that concludes our first Simio tutorial, where we created a seaport with writers arriving and we determined the operational characteristics.